Hi students, good morning. Welcome to Go Vidya. As part of previous year questions, today we are going to solve some more questions related to the electrical transformers. Let's look into the question. The question is given about a 100 kVA 2000 by 200 volt single phase two winding transformer is to be used as an auto transformer for stepping up the voltage from 2000 to 2200 volt. The ratio of full load losses as an auto transfer to two winding losses. Okay, after reading the question, what they are asking, the ratio of the ratio of the ratio of full load losses of an auto transformer to two winding transformer. That means the copper losses. They are asking the ratio of auto transformer copper losses to the two winding transformer copper losses. Okay, the concept is about auto transformer. What is the concept? Concept is about auto transformer copper losses. Auto transformer copper losses. Okay, let's see the formula. What we know related to auto transformer copper losses in comparison to the two winding transformers. Auto transformer copper losses equal to 1 minus k into copper losses of two winding transformer. Copper losses of two winding transformer. Then the ratio of these two will be, therefore auto transformer copper losses divided by two winding transformer copper losses is equal to 1 minus k. We need to find out the k from the given data. What is the formula for k? K is nothing but L LV by HV. Okay, what is the LV? It is what they are telling. The auto transformer configuration is 2200, or this is the output voltage and 200 may be the input voltage. Okay, LV is 200, HV is 2200, it will be 11. So therefore from equation 1 1 minus k equal to 1 minus 1 by 11. It will be 11 minus 1 by 11, that will be 10 by 11. Our option is C. Is it clear? Okay. The question may be lengthy, but the solution will be very simple if you have the formula of comparison of copper losses of auto transformer to two winding transformer, and K. K is the transformation ratio or percentage stepping, you can say. If you know these two, you can solve the question easily. Okay, let's move on to the next question. The next question is about which of the following statements are true in case of delta delta connected three phase transformer. Okay, delta delta connected three phase transformer that asking. We'll see the options. The first option is about the cross sectional area of each turn winding is small. They are telling cross sectional area of each turn is small. Let's examine this option whether it is true or not. So if you see in a delta connected transformer, the parameters, since they are asking about the winding cross section, we need to look about current parameter. How is the current parameter? In delta connected transformer, phase current is nothing but IL by root 3. IL by root 3. That means whatever the line current is there, that is going to be divided by root 3. Root 3 times less current will flow in the phase windings. Okay, less currents will flow in the phase windings. So what is going to happen if current is less? If current is less, the diameter of winding, or you can say it as cross sectional area of winding will be less. Cross sectional area of winding will be less. Okay, since it is going to carry very small current, so the diameter of the winding is going to be reduced. Okay, thereby cross sectional area will be less. So first option is correct only. Let's look into the second option. Windings require more number of turns. Windings require more number of turns. We'll examine this. They are asking about number of turns. Number of turns is directly proportional to the voltage. Okay. See, in delta connected system, what is the relation between the line voltage to phase voltage? Line voltage to phase voltage, it will be equal. Line voltage equal to phase voltage. Okay, if you, in comparison to the star connected network, what will happen? Line voltage is equal to phase voltage is equal to VL by root 3. So in comparison to the star network, the delta connection may require more number of turns to generate more voltage in the windings. Okay, so windings require more number of turns in comparison to the star winding. Okay, this is also correct. Can be used for small HV transformers. No. If you are going for high voltage, if you want to increase the voltage, means number of turns will get increased. Okay, this is not economical. Number of turns means windings will get increased. Cost of the copper will get increased. Size of the transformer is going to be increased. So it may not be economical. So this option is not correct. Let's see into the fourth option. Can be used as V connection. Oh yes, we already discussed V connection or open delta connection. We can operate delta transformer. We already discussed in the previous sessions. So among the given options, the correct answers are 1, 2, 4. Let's see which option is suitable for us. 1, 2, 4. 1, 2, 4 is D. Is it clear? Let's move on to the next question. The next question is about three single phase transformers, each of 100 kVA ratings, are connected in delta. If one of the transformers is taken out of service, the capacity of the system will be, okay, what they are telling, each capacity is 100 kVA, are connected in delta. Now what will happen? One of the transformers is taken out of service, maybe due to some fault, some other reason. What they are asking, final capacity of the system. We already discussed. Well, let's look into the concept. What they are telling, initially it was delta connected. One transformer is taken out, it become open delta. So they are asking capacity of open delta. Let's look into the formula. We already derived the formula from the previous sessions. So now we will go directly to the formula. We know that percentage of open delta equal to 0.577. We can write it as 57.7% of delta system. Okay, so therefore total kVA, since they given individual, each kVA they given, so we need to find out total kVA of delta connected system. It will be 3 into each transformer kVA. It will around 300 kVA. Let's take it as equation 1. So they given in kVA, so no need of so we need to convert this into numerical value. From equation 1, what you can write, capacity of open delta system equal to 0.577 into 300. After multiplying this, how much you will get? It will come approximately around 173.2 kVA. Okay, so our option is B. Our option is B. This formula we already discussed in the previous sessions. You can you can refer the previous sessions if you want a derivation of that formula. Okay, is it clear? Let's move on to the next question. Okay, the next question is about the efficiency of a 60 kVA transformer is 0.96 at full load as well as at half load. For this transformer at full load, the copper losses is less than, more than, equal to the core losses. They are asking comparison between copper losses and core losses when the efficiency is 0.96 at full load as well as half load. Okay, you have to, if you look into the efficiency curve with respect to load current, it will be like this. Okay, the maximum efficiency will occur when iron losses is equal to copper losses. The efficiency is given as 0.96. Okay, 0.96. They are telling this is the half load and this is the full load condition. Okay, if you see here, towards this side what will happen? Iron losses will be more than the copper losses. Toward this side if you go, it will be copper losses will be more than the iron losses. Now at what condition they are asking? They are asking at full load condition. That means towards this side, what is the relation between the copper losses and the iron losses? So from this efficiency curve, what we understood, at full load conditions copper losses are more than the core losses. Our option is B. Is it clear? Okay, let's move on to the next question. The next question is about the full load copper losses and iron losses of a single phase 90 kVA 115 volt by 230 volt 50 Hz transformer are 1200 volt and 400 volt respectively. What they are telling, copper losses and iron losses they are telling at 1200 volt and 400 volt, and kVA is given as 90 kVA. If the frictional losses are 132 watts, then the total losses when the transformer is operating at 80% full load are. To confuse the students, they made one statement as friction losses are 132 watts. This is a trap. We need to be very clear. In a transformer, there is no moving part at all. Then from where the friction losses will come? Okay, this to misguide the students, the examiner is going to give this type of data in the question. Okay, so we need to be very careful and we need to read the question carefully and need to write down the given data carefully. Okay, then what they are asking, when the total losses when the transformer is operating at 80% full load, we need to calculate the total losses. We need to calculate the total losses at 80% of full load. What is the concept? Concept is about total losses. Concept about total losses of transformer. What is the formula we know? Total losses is equal to iron losses at rated voltage and copper losses at full load current. This is the total losses. Okay, what they are asking, whatever the given, let's note down the given data. First note down the given data. copper losses at a full load is given as 1200 watts. Iron losses given as 400 watts. Okay. So we should not consider the frictional losses. Why? Because in transformer there is no moving part at all. So friction losses won't be there. So to misguide the students, the examiner is going to give such type of data. Okay. So we won't consider the friction losses. Okay. Now what they are asking? They are asking losses at 80% full load. Iron losses will be constant at any load, so iron losses won't change. Okay, only copper losses are going to varying with load, so we need to calculate copper losses at 80% of full load. 80% of full load we need to calculate first. So we know that copper losses at any fraction of load x is given as x square into copper losses at full load. Okay, this is written as, where x is given as 0.8. Okay, x is given as 0.8. That implies 0.8 whole square into 1200 watts. It will be 0.64 into 1200 watts. How much it will come? Let's calculate. So the total losses will be, how much will be the total losses? Total losses equal to iron losses plus copper losses. It will be 400 plus 768. How much it will come? 1168. It is near about option B. So our option will be B. Okay, let's move on to the next question. Okay, the next question is about a 20 kVA single phase 50Hz 2000 by 200 volt two winding transformer is connected as an auto transformer so as to achieve a voltage ratio of 2200 by 200 volt. What will be the rating of this auto transformer? What will be the rating of this auto transformer? So they are asking about rating of auto transformer when two winding transformer is reconnected as a auto transformer. Okay, what is the concept about? The concept is about rating of auto transformer. Rating of auto transformer. Okay, we know that rating of auto transformer can be written as rating of two winding transformer into secondary voltage divided by common voltage. Secondary voltage of auto transformer divided by common voltage. Okay, so what is the rating of two winding transformer given? 20 kVA. Okay, Secondary voltage, that means if you see, it is converting as to actually we need to consider it as a first step up transformer. You need to take it as step up transformer. Why? Because the rating will be same for both step up and step down. For easy calculation, we need to consider it as a step up transformer. That is 200 to 2200 volt. Okay, 200 to 2200 volt. So then the secondary voltage will be 2200. What about the common voltage? Common voltage will be 200 volt. Okay, let's do the calculation cancellations. Wait. Rating up to given as 20 kVA. Okay, you have to take it as in 20,000. Voltage is in volts. Okay, be careful about the units. Don't get confused. Let's do the cancellation. 11. Okay, it will be 22 kVA. 22 kVA. Therefore, the rating of auto transformer is 22 kVA. So option is C. Option C. Okay, let's move on to the next question. The next question is about, in a three-phase transformer has 600 primary turns, 150 secondary turns. 600 primary turns and 150 secondary turns. If the supply voltage is 1.5 kV, determine the secondary line voltage on no load when the windings are connected in first case delta star, second case star delta. Okay. First, let's note down the given data. They given the tons, so we have to note it down. These are phase turns. N1 is equal to 600, N2 phase turns is equal to 150. Okay. Supply voltage, that means E1 is given as 1.5 kV, that means 1500 volt. 1500 volt. Okay, so the first case is about delta star. In delta star, what is the secondary? Secondary is a star. Secondary is star connection. Why we need to see the type of connection? They are asking the secondary line voltage. Secondary line voltage when it is in the delta star connection. So secondary side is star connection. First we'll calculate the phase voltage. E1 per phase is equal to E2 per phase N1 by N2. From this E2 is equal to N2 by N1 into E1. What is N2 given? 150. N1 is given as 600. E1 is 1500. Okay. After this calculation, how much it will come? What is it? E2 per phase will be, how much it will come? This 0 0, so you can calculate 225 by 6. 225 by 6. Okay, but in star connection, line voltage E to L is equal to, how you have to calculate? E to L is equal to root 3 into E to phase. E to phase. Therefore, this is E to phase. E to L is equal to root 3 into 225 by 6. How much it will come? After calculation, we will get around 649.5 volt. Okay. If you observe the options, there are two options are matching. So you have to do calculation for second one also. Okay. The second connection is star delta. The second connection is star delta. So the secondary winding is delta. In delta connected system, E to L is equal to E to phase. Line voltage is equal to the phase voltage. So E to phase, how much it will come? E to phase, how much it will come? N2 by N1 into E1. It will come around E2 per phase is equal to 216.5. Okay. So the option is B. Okay, let's move on to the next question. Let's move on to the next question. The question is about, if load current of single phase ideal transformer leads secondary terminal voltage by an angle, actually this is 30 degrees, typing mistake I think, and no load current lags supply voltage of 10 degrees, then the angle between no load current and load component in primary current under ideal condition is. Okay, in order to solve this type of question, we need to remember the phasor diagram of the transformer under loading condition. Let's draw the phasor diagram. This is the flux. When this will be the IW, and this will be the supply voltage V1. This will be the magnetizing this will be This is magnetizing current. This will be the iron loss component. The resultant is I0. The resultant is I0. In secondary side, if you see, this will be the V2. This will be E1 comma E2 induced EMF. Okay, they are telling at leading. What they are telling? The secondary terminal voltage. Sorry, the load current is lead by secondary terminal voltage by 30 degrees. So load current, whatever they are telling, I2 is leading by at an angle 30 degrees. Okay, leading by 30 degrees. What they are asking, we need to shift this load current to the primary. It will be exactly opposite. If you shift the load current to the primary side, it will be out of phase. That means this is the load component I2 dash shifted to primary. Now if you see, whatever the angle is difference between I2 and V2 will be the same between I2 and V1 also. Okay, I2 and V1 also. This will be pi equal to 30 degrees, and they given 10 degrees as the angle between V1 and I0. This is, they take it as theta, it will be 10 degrees. Now what they are asking, the angle between load component in primary and ideal condition. Ideal condition means no load condition. Okay, so now what will be the total angle? Theta plus pi. Theta plus pi equal to 30 plus 10, it will come around 40. It will come around 40. So third option is B. Option is B. Is it clear? If you understand the phasor diagram of transformer, you can solve the question easily. Let's move on to the next question. The next question is about match the following conditions regarding parallel operation of two transformers. Regarding parallel operation of the transformer. So they are asking necessary and essential conditions. Okay, necessary and essential conditions. We need to understand the first meaning of essential condition. Essential means these conditions are mandatory. Mandatory. Necessary means these conditions will be suitable. Suitable conditions, you can say suitable. Okay. First, the transformer need to meet the mandatory condition to operate in parallel. Later we need to check out the necessary condition. Okay. The first mandatory conditions. What are the mandatory conditions? Polarity. Polarity must be same. Polarity must be same. Phase sequence must be same. Phase sequence must be same. And what other thing? Vector group must be same. Vector group must be same. These are the essential conditions. Let's see the different options given first. Vector group also given, polarity also given. Okay, essential condition, two conditions are given. But we need to choose most suitable options. Both options are essential conditions only. But in options, if you observe A, B, C, D, only they selected. So we need to see most appropriate option. Okay, these two will be, both are essential conditions. Among those, which one will be more dangerous? Okay, more must and should we need to check is polarity. Okay, why means if polarity change, the transformer will get short circuited. Okay, if polarity change, the transformer will be dead short and it will draw very high currents and it will get burst out. But if vector group is not same, what will happen? If vector group is not same, circulating with currents will form. Okay, circulating currents will flow inside the transformer. After some time, the heat will get generated. But compared to the polarity, vector group priority may be somewhat less. Why? Because even though vector group is not same, so the transformer can operate in parallel, but there is a circulating currents inside the transformer. This will leads to more losses and heat generation, and at last that condition also transformer may get burst out. Okay, among those two, the most suitable option for essential condition is 3. Okay, going to the necessary condition. What are the different necessary conditions? Percentage impedance, percentage impedance must be percentage impedance need to be same. Percentage impedance need to be same. And KVA rating, turns ratio, KVA rating and turns ratio need to be same. Turns ratio need to be same. Okay. If you observe the options, the essential condition also having 3 options: turns ratio, percentage impedance and KVA rating. But you have to select the most appropriate option. Okay, most appropriate option. The most appropriate option for necessary condition is KVA, same percentage impedance. Why you need to choose only percentage impedance other than options means the load sharing is directly proportional to the percentage impedance. Okay, sorry, inversely proportional to the impedance. So if same percentage impedance is not there, okay, if same percentage impedance is not there, then what will happen? The load sharing will get disturbed. Okay? So among the given options, we need to select the most appropriate option. The most appropriate option is for necessary condition the percentage impedance need to be same. So our option will be A is equal to 4 and B is equal to B3. Option itself not given. I think this may be typing mistake may be there. This will be A, this will be B. Okay, sorry. This will be A, this will be B. So our option will be B. Essential condition, same polarity. Necessary condition, same percentage impedance. Okay, let's look into the next question. The next question is about at no load, a single phase transformer, a plot is drawn between watt to frequency, where F is frequency and W is wattmeter reading. If C is intercept and y-axis and M is slow, then hysteresis losses and eddy current losses are given by. We know that hysteresis losses equal to KH, which is a constant, F into B max X. Eddy current losses equal to KE into F square B square. From this, If V by F is constant, if V by F is constant, in general V by F of the transformer is going to be constant. So then B max is also be constant. Therefore, hysteresis losses are directly proportional to F, iron losses are directly proportional to F square. This can be written as, let's take a constant A, iron losses can be B into F square. Therefore, total losses W can be written as WH plus WE. That is AF plus BF square. If you take the frequency out, A plus BF. Okay, it is similar to the equation y is equal to mx plus c. Y equal to mx plus c. Okay, where y is the W by F and c is the A and mx is BF. Okay, therefore C is nothing but hysteresis losses. What they are telling? First, hysteresis losses. C is nothing but hysteresis losses MF is nothing but eddy current losses. Eddy current losses. Clear? So option will be C. Option will be C. Let's move on to the next question. The question is about dielectric strength in kilovolt per mm at 50 Hz in the increasing order of strength of the following material. Okay, they given three different type of materials. One is porcelain, another is transformer oil, another is mica. If you see, porcelain will have the high dielectric strength. In general, porcelain will have the high dielectric strength comparatively transformer oil and mica. That's why porcelain we are going to use in the transformer bushings. Transformer bushings. Transformer oil also having some dielectric strength, but it will be less compared to the porcelain. Why? Because the transformer dielectric strength will be around in the range of 70 to 100 kV, 70 to 100 kV only. Okay, whereas porcelain will be, it depends. Okay, it depends on the, for suppose if you take at the rate 400 kV transformer, the porcelain bushing need to withstand for at least 230.9 kV. That means phase voltage. Okay, it has to withstand for 230.9 kV. Whereas transformer oil we need to withstand for 70 to 100 kV. Mica is very less. It will be in the range of some kVs, some small kVs. Okay, so the comparison will be, first porcelain will be there, after transformer, after that mica. So option will be A. Is it clear? Okay, so if you compare the materials according to their dielectric strength, porcelain will have the high dielectric strength comparatively to the transformer oil and mica. So our option is A. Let's move on to the next question. The next question is about the self and mutual inductance in henries of two coupled coils. Two coupled coils are L1 and L2 given. Okay, L1 and L2 given, and mutual inductance M12 and M21 given. Okay, currents I1 and I2 given. The mechanical work done in decreasing x from 1 to 0.5 meter is watt second. Okay, they are telling about work done. Work done is nothing but energy. Okay, energy required to bring the 1 to 0.5 mm. Okay, so we need to calculate the energy. You know that energy stored in the inductor is given as half Li square. When they given the mutual inductance also, the energy stored will be written as half Li1 square plus half Li2 square L1 I1 half L2 I2 square M12 I12 I1 I2. Okay, first we need to calculate the energy at when x is equal to 1 and when x is equal to x is equal to 0.5. Then we need to subtract when total energy at x equal to 1 minus total energy at x equal to 0.5. So we will get the answer after doing this. Let's do the calculation. First, total energy ET can be written as, from the given data, half 5 plus 1 by 4x into 20 square 1 by 2 3 plus 1 by 4x minus 10 whole square plus 1 by 4x 20 into minus 10. At x equal to 1, how much we will get? Just substitute x is equal to 1 in the equation. We will get it as 100 by 2, 21 by 4, 13 by 4 minus 1. After solving this, we will get it as 162.5 joules or watt per second. At the rate x equal to 0.5, ET you can let's take it as equation 1. If you substitute x equal to 0.5 in equation 1, how much you will get? 1 by 2, 21 by 4 into 400 plus 1 by 2, 13 by 4 into 100 plus 1 by 2 into 1 by 4 minus 200. It will be around 175. Therefore, if you observe this, the total energy in decreasing nature. Okay, so from 0.5 to 0.1, so total energy required for doing the work to bring the 1 to 0.5 is 175 minus 162.5. It will be 12.5 watt second. Our option is D. Our option is D. Is it clear? We are having one more option, minus 12.5 also, but Why not taken the negative sign? They are telling they bring already they mentioned it is in a decreasing nature 1 to 0.5. So again no negative sign not required here. We'll move on to the next question. Which of the following statements are correct? The concentric coils are used in core type transformer, whereas interleaved coils are used in cell type transformers. It is the comparison between the concentric coil versus cell type transformer. In general, we know that in cell type transformer, we are going to use interleaving coils to reduce the leakage flux. Cell type transformers, we are going to use interleaving coils to reduce leakage flux. Okay. And one more comparison they are asking about power levels. Normally cell type transformer is preferred for low power level, and core type is for high power level. Okay. So the suitable option is first one is correct. Concentric coils are used for core type, interleaving coils used for cell type. Interleaved also called it as sandwich type coils. Okay. And coming to option R, cell type transformers are preferred for low, yes, core type are used for high power losses. Okay, so our option will be P and R. So option is A. Let's move on to the next question. The next question is given about which of the following statement is not true with respect to a single phase transformer. That means if the load current is kept constant, the maximum efficiency occurs at UPF. The transformer efficiency is maximum at same load current regardless of the variation with the load power factor. Okay. The load current is kept constant. The maximum efficiency occurs at 0.8 power factor lagging. D. The core losses and copper loss of the transformer are unaffected by variation of the power factor. We will see option by option. First one is if the load current is kept constant, the maximum efficiency occurred UPF. So we will write it. We will draw the efficiency curve between the when at the rate load current constant, efficiency curve with respect to power factor. If you draw, it will be like this. The maximum efficiency will get at UPF. It will be 0.8, 0.6 like that. Okay. Maximum efficiency will get at the power factor. So option A is correct. UPF only you will get the maximum efficiency. Second option is transformer efficiency maximum at same load current regardless of variation with respect to load. We have to draw the efficiency curve with respect to load current and variation of the power factor. Okay, this let's take it is for UPF power factor it may be this, and this may be 0.8, and this may be 0.6, and this may be 0.4. 0.8, 0.6, 0.4. If you see, the maximum efficiency will be at one current only. Okay, Ix, that is X at maximum efficiency. Okay, so option B is correct. The load current is kept constant. The maximum efficiency occurs at 0.8 power factor. From this curve we can say this is wrong. Maximum efficiency will occur only at UPF when load current is constant. Is it clear? Okay. The next option is the core loss and copper loss of a transformer are unaffected by variation of power factor. If you observe the core loss and copper loss, core loss depends on voltage, copper loss depends on current. It is independent of the power factor. So this option is wrong. What they are telling? Not true option you have to select. Okay, not true option is D. This is our answer. This option is not true. Is it clear? Let's move on to the next question. The next question is about the full load voltage drops in a single phase transformer are 3% and 4% due to resistance and leakage reactance respectively. The full load power factor at which voltage drop is maximum and the load power factor at which voltage drop is 0 are. They are asking voltage drop is maximum and voltage drop at 0. At what power factor it is going to happen? Let's see. We know that if you observe the voltage curve like this, the maximum voltage regulation will occur at a lagging power factor, 0 will occur at a leading power factor. Okay, this is percentage regulation versus power factor graph. Okay, let's calculate the first. We will give for the maximum efficiency. Okay, they given as percentage R is 3%, percentage X is 4%. At maximum voltage regulation, cos pi is given as percentage R divided by percentage Z. We have to calculate Z. Percentage Z is nothing but R square plus X square. That means 3 square plus 4 square. It will be 5. So therefore cos pi is equal to 3 by 5. How much it will come? It will come 0.6. So 0.6 it should be lagging. So for getting voltage regulation max, the power factor need to be 0.6 lag. So what are the suitable options? There are two options are there. Okay, A and B are the matching with our requirement. But if you observe the A and B carefully, 0 voltage regulation will occur only for leading power factor. So our option will be B only. Okay, our option will be B. Is it clear? How we solve this question? We solve this question with the help of the regulation curve and the at maximum efficiency power factor condition. Okay, by using these two we solve the question. Okay, by this we are going to end up the today's session. Tomorrow we'll inform whether we'll have the class or not. Okay, our team will post in the updates in our Telegram group and WhatsApp group. Okay, be in touch. If you have any doubts, you can contact our support, our contact number as shown on the screen. We are ready to help.